In this video, I'll be talking about generating function, and here I am discussing these generating function for the counting problems. So we have already discussed some of the concepts about permutation, combinations, with repetitions, without repetitions, and also we have talked about the distribution problem. And another tool that we can look for the counting problem is the generating functions. So to look at what are the generating function and its connection to the partition of integer. So a lot of generating functions are developed in view of the partition of integers, and this was initially started by Euler in 1748 in this connection to study the partition of integers. So we will look at what are the generating function and how we can use these in the counting problem. In fact, we can also simply see the generating functions are simply the power series, or we can say that these are simple Taylor series, and we leave here the questions of the convergence. So most of the power series that we take convergent. So now to define what are the generating function, let me to write the question. So most of the time our obvious question is of this type: what is the generating function of the sequence, generating function for the sequence. So we may have a sequence A0, A1, A2 and so on. So if we happen given a sequence, we must need to know what is the generating function. So generating function is some f of x which when open as a power series give rise to these numbers. So we defined formally in connection to this question what is the generating function, and for the generating function let me to consider a sequence, and the general notation for the sequence is AR. So this consists of the sequence numbers A0, A1, A2 up till AR and so on. So this is the rth term, rth number in the sequence, or we can show it by this type of the brackets, or we can use it open parenthesis to show the sequence. This be the sequence of numbers, or we can say, let us say this is the sequence of numbers. Then the ordinary generating function. So I'll say ordinary generating function. Why I'm specifically saying ordinary generating function? Because there is also another type of the generating function which we call exponential generating function. So here when I say the generating function, which means we are talking about ordinary generating function and not the exponential. So the generating function for the sequence AR is defined to be the power series. This is defined to be the power series, and since I want to create a power series, so I will attach some coefficient. I will attach the power with the variable x, and I will denote it by, let's say, ax. This, just like here I have written this is a function of x, I am simply writing ax, and this is a0 plus a1x plus a2x square plus on up till ar x square, and we continue. So here what I mean is the first term in the sequence that is considered as a constant term, or we may say that this is multiplied by x to the power 0, and then we have x to the power 1 as a coefficient square, x to the power r, and continue. And to write that in the summation form, I can write it as summation r vary from 0 to infinity ar x to the power r. So we are looking that ax is the generating function for the sequence AR. So I will call ax is the generating function. This is the generating function for the sequence AR. So this is what we mean by generating function. Now to understand this generating function, let us take an example. So in this example, I want to find the generating function for the sequence of ones, and these ones goes to infinity. So as I've just explained, we know that this is A0, this is the value for A1, and here it is A2, and we continue reading like this one. To find the generating function, let's first create a power series. So A0 is a constant term into A1 x to the power 1 plus A2 x square plus on. And I can also write this as summation AR x to the power r varying from 0 to infinity. So this is the generating function. And if you substitute these values, we get A0 is 1, A1 is also 1, x to the power 1, A2 is also 1, x square, and we continue. This means the series is 1 plus x to the power 1 plus x square plus x cube and so on. Now we can notice that this is a geometric progression. or we can simply say that this is a geometric series, and here the common ratio is x. And we also notice that we assume that these power series are convergent. So assuming that mod x is less than 1, the series is convergent. And for this we can apply the GP formula, and here we get the formula as if we have a GP series, then this for the infinite series the formula is the first term upon 1 minus r. R here is the common ratio. So using this formula, the first term here is 1 and here the common ratio is x. So I will write it as 1 over 1 minus x, and this becomes a function of x, and here I can write this as a of x. So we can say 1 over 1 minus x. In fact, we can also call this as a closed form. So sometime we say this as a closed form. So this is the generating function. So when I open this function as a power series, this gives me generating function of the series of the sequence of ones. So this is what we mean by the generating function. Now our question is in the counting problem. Sometime we have numbers here. These are the counting numbers due to certain conditions, due to either permutation or combination or coming up from the distribution problem. We do need to identify what is the function which generate these numbers. Let's take one more example. And for the larger scale, we must need to understand some of the basic properties of the generating functions also. So we'll do one example and then I'll talk about the basic properties. So in this example, I want to find the generating function for the sequence n choose 0, n choose 1, n choose 2, n choose n, and then there are some zeros later on. So this is not an infinite sequence, rather this is a finite sequence which is made to be infinite if we add the remaining terms as a 0. So again, if I want to write, I will write it as summation r goes from 0 to infinity a r x to the power r. And we notice that this is a naught, this is a1, this is how it is always given, a2 and so on. So to start looking at the generating function, we know the first term is n choose 0. Then the next term should be multiplied by the variable x. So this is n choose 1 multiplied by x to the power 1. Then we will take n choose 2 multiplied by x square, and we continue doing like this, n choose n, then x raised to power n plus, now here you can see that this is 0. So for the remaining term we have 0, n plus 1 plus 0 into x to the power n plus 2 and so on. So all the other terms are 0. So that means we get a finite series here. So this is initially infinite, but this infinite series turn out to be finite. So we can write it like summation r goes from 0 to infinity. And if I want to write this again in terms of this expression, so currently we have n choose r instead of ar. So ar is my n choose r, and then I have x to the power r plus, okay, so here I want to make a change. So this is r goes from 0 to n, because till n choose n, I have the last term till n choose n. Whenever I will need to take for the remaining term, so summation, because here you have written till infinity. So for the next sum, r varies from n plus 1 to infinity. So this total summation 0 to infinity, I have split it into first class where I am taking r goes from 0 to n, and then I am taking n plus 1 to infinity. Now for n plus 1 to infinity, the value for ar is a 0 into x to the power r. Okay, so that makes sense. And now this term is completely 0 and I'm only going to look at this one. Now this is simply using the binomial expression. This is 1 plus x to the power n. We know that if I look at using binomial theorem, so if we use the binomial theorem and if I want to find what is 1 plus x to the power n, we know that this is summation r goes from 0 to n choose r, x to the power r. So that means for this power series we have this expression. So we get 1 plus x raised to power n. This is the generating function for n choose 0, n choose 1, this is a sequence, n choose 2 up till so on, n choose n. So this is a finite sequence actually, which we have written initially for as an infinite sequence. So any finite sequence can be written into infinite sequence by turning the remaining term as 0, and this acts as a generating function for this problem. Now consider this example, and in this again I want to find the generating function for the sequence AR for each n belongs to natural number including 0. So that's basically whole numbers, where AR is 1 whenever R is equal to n, otherwise it is 0. So in this case, say I want to write now the generating function, so I will again use the same formula. R goes from 0 to infinity, and if I open this as a power series, I got a0 a1 x to the power 1 a2 x square plus a3 x cube plus so on, and then I will have ar x to the power r and plus so on up to infinity. Now it is said that whenever r is equal to n, this value is 1 and otherwise it is 0. So whenever r is equal to n, let me to also write here one more term. Say for example, we have an x to the power n and plus so on. So whenever r is n, this value, so here it is general R. So whenever R exactly reaches to n, so in that case I am going to write this value as 1, and for the remaining other position it will be 0. So we will have 0 plus a 0 plus everywhere it is 0, except when this general value will become 1. So in that case I will take an equal to 1 and I will have x to the power n, and for all other terms again it is 0. So we can see that this gives rise to a sequence. If I want to extract a sequence from here, so we will say the sequence is of the type 0, 0, 0 and continue doing like 0, this is 1, and then again we have a continuation of 0. Only at the nth position I have single 1. And for this case, I have a generating function, and this is simply x to the power n, because the power series leaves me only this generating function x to the power n. So I can say, if this is the function a of x, so I will say ax, which is equal to x to the power n. This is generating function for sequence, which is star. So that's the answer we can going to say. So now we talk about the properties and operations on generating function, and for this let me to define the two generating functions. So let me to just consider the two generating functions. So let ax and bx, this be respectively the generating function for the sequence, generating function for sequences AR and BR. So I have considered two sequences and I have considered their generating function. So we can write ax equal to a0 plus a1x plus a2x square plus so on. This is one of the series, so that is summation ar x raised to power r. R varies from 0 to infinity, and the second is the generating function bx for the series, for the sequence br, and in terms of the series we have b0 plus b1 times x plus b2x square plus so on. That is same as summation r goes from 0 to infinity br x to the power r. So we will first define the sum and then we will define the product. So to define the sum, we will write the sum ax plus bx, and this will also give us the summation of the two power series is also a power series, and here we are going to do the component wise sum, or we may say the like power of the x are going to sum. So we will have ax plus bx, this is equal to a0 plus b0, the constant terms, plus a1 plus b1 into x plus a2 plus b2 into x square plus so on. And in general we may write ar plus br x to the power r plus so on. And this we can always write it as like c0 c1 x to the power 1 plus c2 x square and plus so on, where we can always write that cr, this is ar plus br. So cr will be a general rth term in the sequence of this, and let me to denote it by cx. So this cx is the new power series, or we can say this is the generating function for the sequence of c0 c1 c2, where cr is the sum of ar plus br. Now similarly we can define the product, and for the product we will take ax into bx. And for the product we will use the property that we generally call it as convolution property. So we will see what is the convolution property also. So the another general name is for this is convolution property. So when we multiply this, I am going to write this as ax into bx. Let's say this give me another power series, that is dx, and that's a closed form, and I am writing d0 d1x plus d2x square plus so on, just like the one that I have obtained here. Similarly, there will be a power series that will come after taking the product of ax and bx, and I'm denoting that by dx. So this will be power series something like this one. Now what are the values for this one? So as we have added CR, that is AR plus BR, what will happen in D naught D1x? So we can notice first AX into BX. So if I have this power series, we can see that this is infinite power series. A2x square plus A3x cube plus on 1 is this, and then I'm going to multiply this by B0 plus B1x plus B2x square and plus on. Now if we multiply, let's say I want to multiply A0 with all this term, then I will multiply A1 times x with all this term, and then I will multiply A2x square with all these terms, and then A3x cube with all this term, and continue doing like this. And then we club the like terms. So when we follow this procedure, what do we get? We get A0 into B0. That's because of the first term which is constant. When this A0 is going to multiply by this B1, so we will have A0 B1 into x. So this is the term. And when this A0 is going to multiply with this one, so we are going to get A0 B2 x square, and continue doing like this because there will be some more terms here. Then we multiply this A1, then we multiply A1x with B0. So here we get the term A1 into B0 times x plus, then this A1x will be multiplied by B1x. So this will be A1 times B1x square and plus on. So what we notice is that there are terms which we are getting like powers of x from the different products. So now if we club, we get A0 B0 as constant plus, look at this x term and also look at this x term. So we get A0 B1x plus A1 times B0 x. And similarly, when I look at x square, this term and this term, there will be one more term. Say suppose I take A2x square multiply by this B0. Still I am going to get the coefficient x square. So let me to write this term also, A2x square, and there we also have a B0. So if I want to see what is the coefficient of x square, and then similarly you can see the coefficient of x cube, this comes due to the three terms, this x square, this x square, this x square. That is A0 B2 plus A1 B1 plus A2 B0. Okay. Now this property in general, if I want to write the general rth term, what will be the general rth term? So for this general rth term will be, first let's write it in the same direction. If this is 0, it goes maximum to 0. If it is 0 and here it is first term, then we'll have A1 B0. 0 2, then we will have 1 1, then we have 2 0. So all possible combinations are coming with one integral value less. So if I want to take the rth term, say for example I have A0 BR, and this is because of this BR, I am going to definitely get the coefficient of x to the power r, because this is how you must have multiplied BR into x raised to power r is multiplied by the first constant term. So we still get x to the power r. Then its first coefficient, that is A1. So from here you get x to the power 1 and 1 less from this one. So that is BR minus 1. From here you will get the coefficient of x to the power r minus 1. Now together they will again make the x to the power r coefficient. So this way we will continue, and this product will continue until we get AR B0. So this becomes the rth term. And this property we call convolution. So if I specifically want to rewrite this term, let's call this as delta. So can I write, so where we can write A0 BR plus A1 BR minus 1 plus on plus AR B0. This term can be written as summation. K varies from 0 to R, aka BR minus K. Now we can notice it that, say for example K is a 0, here K is a 0. So the next term will be BR. If K is equal to 1, so the next term will be BR minus 1, and we are getting the desired number. When K is equal to R, so the term will be AR, and here you will have B0. So all these terms are coming, so we can write that into this summation. And this particular property, we call it as a convolution. Now we go back here. If in our problem we had dx here, and dx is d naught, d1, dx. So we can say this is number 1. What will be the general term dr here? So now we can say dx, which is the product of ax and bx, and that was, we have written d naught plus d1x plus d2x square plus so on so on so on plus dr x to the power r and plus on. And we have noticed that from the delta, from this delta, we have noticed the rth term. So what is the rth term here? So we can say where dr, this is equal to summation k goes from 0 to r, ak into b to the power r minus k. So that's how we can define the product also, and this is what we are called either the Cauchy product also, or we can call this as a convolution of the two sequence AR and BR. Now with this we also define two more standard results, which is due to the binomial theorem. And for this, let me to first define generalized binomial coefficient, because often in the generating function we do require some terms like this, or maybe in terms like this. Now there is a difference in this term and this term. Here this term is in the numerator, so we may take n as positive. Say suppose n is something like positive, I want to evaluate something like this one. This is going to give me a finite expression. But if I have some term here in the denominator, say for example I have a 4, and in the numerator it will go 1 minus x to the power minus 4. This is going to give me an infinite term. So by looking whether I have n here positive or negative, to calculate this quantity in general, let me to define the binomial coefficient, which is generalized binomial coefficient here. And for this I'll take alpha belongs to real and r belongs to set of natural number. So we defined generalized binomial coefficient, and the notation is same as we use in the previous case, but in this case now we are taking alpha choose r, and alpha can take the negative value. So we put alpha choose r, this is equal to alpha choose r divided by r factorial, where in this case I am defining alpha choose r. For the generalized case I am writing this as alpha into alpha minus 1 into alpha minus 2 up till so on alpha minus r plus 1, and we also set alpha choose 0 equal to 1. So now whenever you have a negative quantity, so you can take, let's say for example alpha is minus 2, so this will be minus 2, this will be minus 3, this will be minus 4, and continue doing like this. So we can write down this expression, and for this case once we have set up this system, we can write 1 plus minus x raised to power alpha. This is equal to summation r goes from 0 to infinity alpha choose r plus minus x to the power r. And if I open the series, we get same 1 plus minus alpha x plus alpha into alpha minus 1 divided by 2 factorial x square plus minus alpha into alpha minus 1 into alpha minus 2 upon 3 factorial into x cube plus on. The general term will be minus 1 to the power r alpha into alpha minus 1 and so on alpha minus r plus 1 divided by r factorial into x to the power r plus on. So in case you want to take a particular value and substitute into this one, you will see that this reduces to the same formula that we are already doing for the binomial coefficient. So we also note here one more identity, and all these identity may be required for the generating functions, for a little more complicated generating function. We also know that there is a identity which is, we call it as Pascal's identity, that can be used frequently. So I'm just recalling here in this case, and alpha belongs to r and r belongs to set of natural number. We also note, so let's just bullet these point. So when we take this value 1 over 1 minus x, and if we take alpha equal to 1 in the previous example, we definitely get 1 minus x to the power minus x. So this power series we should already remember always. This I have also explained in this video. This will generate the sequence of ones, and if you have 1 minus x to the power square, this will give me 1 minus x to the power minus 2, and if I apply the previous formula, this will generate the set of natural numbers. So 1 plus 2x plus 3x square plus 4x cube plus so on. Okay. And if I look at one more generalized case, say for example, I want to take 1 over 1 minus x to the power n, and here you already know that n is a positive integer. In this case, say I have 1 minus x to the power minus n, We can also use this as a formula, 1 plus nx plus n into n plus 1 divided by 2 factorial into x square plus n into n plus 1 into n plus 2 divided by 3 factorial into x cube plus so on. I can also write this as 1 plus n minus 1 choose 1 times x. So this n can be written into this form of the binomial coefficient. This can be written in the form of 2 plus n minus 1 choose 2, then x square. This one I can write it in this form, and this is you can see that this has a connection with the distribution problem that we did in the earlier video. So at this moment I'm not explaining because my purpose is to write the generating function. So this connection you can see in the videos where I've discussed about the distribution problem. And for this, of course, you take n belongs to set of natural number. Now, once we have an idea about that these are the power series corresponding to which we can get a closed form. So if I look at the left hand side, they become the generating function of the sequence that we can generate from here. Like here I want to generate a sequence. So the sequence will be set of natural number. Here the sequence would be like 1. This a naught here is this one. This term is a coefficient of x, this will become a1. This is the coefficient of x2, so this will become a2 and so on. And this will become the arth term. Now that means the left hand side generate the sequence a0, a1, a2 up till ar of this type. Now we look at this example before we look at the other properties of the generating function that I will cover it in my next video. And so look at in this example, I've just explained that this is the generating function for 1 over minus x square. So when I open this using the standard binomial formula, here I get 1 plus 2x plus 3x square and so on. So you can say that this is the generating function. This is the generating function for sequence 1, 2, 3 and so on. Okay, so this could be one of the answer. But suppose that you don't remember this formula. In that case, how to derive 1, 2, 3? So what we can do is we can simply remember first few basic sequences. So sequence of ones. Let's see what if this was a sequence of 1. This has generating function. And for this the generating function was simple. Because if I want to write the generating function for this sequence, what I will simply do is I will write a0 plus a1x plus a2x square and so on. And in this case, a0 is 1 plus a1 is 1 into x is per 1, a2 is also 1 x square and so on. So this is simply 1 plus x square, which is a simple GP, and for this we know the generating function is 1 over 1 minus x. Now, so in this case, can I write this left hand side also as summation x to the power n goes from 0 to infinity. Okay, because all the ai's were 1. So here it is summation an x to the power n goes from 0 to infinity. So notice that if all the an is 1, so here the coefficient is 1 simply I have written. So this is summation x to the power n goes from 0 to infinity. So this we can know as a starting result. Now in this case, and let me to call this as simply as f of x also. Now if I take the derivative on both sides, so what I will do is taking derivative on both sides with respect to x, on both sides with respect to x. And here we are not at all talking about the convergence criteria. We are assuming that these power series are convergent. So x, we are talking about only those values in x in which the series is convergent. So now once we take the derivative on both sides, we get f dash x. So this side I am writing on the left hand side. And the power series, that is 1 over 1 minus x, this will become, let's take the derivative of 1 over 1 minus x. This will become 1 over, so minus 1 over 1 minus x square, and then the derivative of the inner term, that is 1 minus x. So you'll get 1 more minus 1. So here we get 1 over 1 minus x square. And now this series, which is also equal to this one, or maybe we can simply look at here. This series, the derivative of 1 is a 0. Then the derivative of this x, this will give me the series as plus 1. And then the derivative of this x square, this will give me plus 2x. And I will continue doing like this, and I will find these terms. Now notice that this is 0, 1, 2x, and if I just simply rewrite the series, I get it like this one, Here now you look and read this as a power series. 1 is multiplied by x raised to power 0, and 2 is multiplied by x to the power 1, 3 is multiplied by x square, and 4 is multiplied by x cube, and so on. So the sequence that you get from these one, all the powers are x are here, it starts from 0. The sequence that you get is 1, 2, 3, 4, and so on. So when I write in the form of a sequence, this is my a naught, which is to be multiplied by x0. This is how it is done. 2 is a1, and that has to be multiplied by x raised to power 1. So we get a sequence of natural numbers. And for this, if I look at the left hand side, what is the function? What is the closed form that I can see? That is 1 over 1 minus x square. So from here also we can simply say the generating function for the sequence of natural numbers, which is written here, natural numbers, is 1 over 1 minus x square. So as you can see that this is one of the property that here I have applied the taking derivative on both sides, and from a standard sequence I have reached to the another sequence. So similar such properties I will be continuing in my next video.